begin our journey into the world of functions, it's so important for us to understand that there is some theory behind this that we need to have a good grasp of. And the first concept we need to be sure of is when we talk about functions and when we talk about relations. So up until now, we've looked at the Cartesian plane and we've understood that you can get x coordinates and y coordinates, and these are considered ordered pairs. And then when we join those ordered pairs up together, you start to form what is either a function or a relation. Now what we'll be learning is that all functions are relations, but not all relations are functions. And we need to know how to tell the difference between the two. The first thing we need to know about is this little thing here known as the vertical line test. And when you do that, you pick up your ruler and you hold it vertically, and then you check. And you have a look at this graph here. You just need to look at one side of the ruler at a time, and you see, does it ever cut the graph more than once? And what you'll notice here is that it is just cutting once each time. So there's only one y value for every x value. And so that means this passes the vertical line test and it is a function. Now let's look at another one. Again, we're going to move our ruler, holding it vertically across this circle graph here. It's a graph we're going to come to know well when we get to analytical geometry. What do you notice, grade 12s? Do you see that the graph is cutting the ruler twice, or the ruler is cutting the graph twice? And as we move along, that continues to be the case, there and there. And so this is not a function, but it is a relation. Since it doesn't pass the vertical line test, it's not a function. Let's have a look at one last contender, this hyperbola over here. So we might think this one is a little bit complicated, maybe a bit too complicated to pass the vertical line test. But let's see. So far we're seeing one cut, one cut, one cut, until we hit the asymptote here, and then what do we notice? There are no cuts happening there, so that's okay. And then suddenly we go back to having just one cut of the ruler. And so this is also going to be a function. So anything that passes the vertical line test can be considered a function. Now you'll remember that we said earlier, all functions are relations, but not all relations are functions. Let's have a look at some types of relations that we should be familiar with. And a good way to test these types is to use the horizontal line test. So I'm going to be using my ruler again to help figure this out. The first type of relation we're going to look at is a one-to-one function. Okay, this is a function because if you were to do the vertical line test that we just learned about, you would see that it would only cut once vertically. And the same is going to be true if we do a horizontal line test. So we hold our ruler horizontally, which is the same direction as the horizon, and then we check. Does it cut more than once horizontally? And as you can see, there's just one cut here, and so this is a one-to-one function where every x value has a unique y value. In other words, the x value here is the only time the y value is whatever it's equal to here. So you could put values in, like -3 has a y value of 5, let's say, and there's nowhere else on this graph where it will equal a 5. So that's a one-to-one function. Next up, we're going to look at this concept of a many-to-one function. So what you will have noticed here is that one x value maps to one y value in a one-to-one function. In this case, we might have many x values that map to the same y value. Let's look at an example of that. Okay, so a many-to-one function is something where you may have two or more x values that map to the same y value. And if you have a look at here, this happens often in a parabola. So we've got an x value here that's mapping to, let's say, a y value of 2. And then on this side, we've got a different x value that is also mapping to that same y value. Now you may be asking, seeing as though we're not passing this horizontal line test, and so it's not one-to-one, is this definitely a function? Okay, so the function test is the vertical line. So what we can do is just double check, and you'll see it needs to pass the vertical line, and it does. It's not cutting the vertical ruler more than once. It was only the horizontal ruler. And so it is definitely a function, but this is a many-to-one function. Many x values mapping to one y value. Finally, we can look at this last type of relation, a one-to-many. Okay, and this is not a function, so be careful. Why is it not a function? Well, how do we test a function? We do the vertical line test. So if we have a look at this one, and believe it or not, this is actually a mathematical graph. You can get the equation of a heart. It's very cool. But what you'll notice is because it's cutting the ruler more than once on this vertical line test, it's definitely not a function. Okay? Why is it not a function? Well, it's not a function because, as said here, an x value is mapping to more than one y value in the range. So here we've got one x value, and this x value says I need to be plotted up here at, let's pretend that's a coordinate of 4, and at the same time that x value needs to be plotted down here at a coordinate of, let's say, -2. And so when that happens, it doesn't pass this vertical line test, and so we know that's not a function. But let's have a look how it performs on the horizontal line test. Okay, so what we notice here is as we move it up, this is cutting more than once on the horizontal line test. So it passes neither the vertical nor the horizontal line test. And this is a one-to-many relation. Now, generally, grade 12s, what we'll do is we will use our vertical line test first to check whether something is a function or not. And once we've decided that, then we'll switch over to the horizontal line test to check whether it is one-to-one or many-to-one. Because if it's not even a function, we're not too interested in the fact that it's one-to-many, because we actually already know that based on our vertical line test. Now, I think we should take some time to just refresh our understanding of functions and function notation. So when we have something like this, f of x, we say f of x, and that means y. That's referring to the y coordinate overall, but it is a function of x. Okay, so f of x is equal to x squared plus 2x minus 3. By now we've done functions so often that the minute we see x squared, we should be picturing a parabola. And then here we've got g of x, so g as a function of x is equal to minus 3 over x minus 2. So when we see the x in the denominator, we start to think of the hyperbola. Okay, the first thing they're asking us to do is to find f of 3 and g of minus 1. What are they actually asking for here? Okay, this is function notation to say, what does y equal when x equals 3? And so what we can do is we can write down that f of x, but in the place of x, we can now substitute a 3. So f of 3 is equal to 3 squared plus 2 times 3 minus 3. And that equals to 9 plus 6 minus 3, which is 12. And so what that means is that somewhere in this function, we have got a 3 and a 12 as one of the sets of coordinates, or one of the sets of ordered pairs. Okay, similarly, they are asking us what is the y value when x is equal to minus 1 in the graph of g? So now everywhere I have an x, I'm going to substitute it with minus 1. So we've got minus 3 over minus 1 minus 2, and that ends up being minus 3 over minus 3, which is equal to 1. And so I would have another ordered pair, or perhaps the first one from this graph, g of x, but the coordinates there would be minus 1 and positive 1. So that's what the function notation means. Okay, another way that we like to word it is we can say when x is equal to 3, it maps to a y value of 12. So there's that mapping way of wording that we also use. Okay, it is also possible to take a y value and determine the x value. So what they're asking now is that we must determine possible values of x if f of x is equal to 5. So what we can now do is we can replace this whole f of x with 5 and then solve. This is simply a quadratic equation, so we can start by moving the 5 over, and that's going to be a minus 5 on the other side. So we'll end up with x squared plus 2x minus 8 equals 0. Then we look at the factors of 8 and how we can use those to make a 2. So 2 times 4. So then we've got our two brackets here. It's going to be x plus 4, x minus 2. And so possible x values here are either x equals minus 4 or x equals positive 2. Okay, and again, we could look at it in coordinate form. We could have the coordinate minus 4 and 5, or we can have the coordinate 2 and 5, and that is definitely a possibility. And then finally, if g of x equals minus 3, determine the possible x values. So let's have a look at that one. We're going to do the same process. So we're going to take the equation minus 3 over x minus 2, and we're going to set that equal to minus 3 because that's what they've given us. Okay, now what we can do is we can do that little cross multiplying trick. So let's put that over a denominator of 1. If I've got one fraction on the left and one fraction on the right, I may cross multiply my numerators and denominators, and it's a very quick way. You can also get a common denominator, and then once your denominators are common, you may drop them on both sides. But I like to use this quick method. So minus 3 times x minus 2 is equal to 1 times minus 3. So we end up with minus 3x plus 6 equals minus 3. Minus 3x equals minus 9. And finally, x equals positive 3. So again, we could say 3 maps to a value of minus 3. Or we could write down the coordinates as open bracket 3, semicolon, minus 3, and close the brackets. It's just so important that you are familiar with this function notation as we move into this next section. Finally, let's look at this concept of domain and range. So domain is the set of all x values for which a function is defined, and then range is the set of all y values that a function maps to. And so what we're going to do is we're going to look at the 4 main functions that we've looked at up until now, and we're just going to check our understanding of domain and range for each of them. Okay, so the first one, the straight line, we have a look which x values are defined here. Well, these arrows are showing me that it's going to go on forever towards negative infinity and on forever towards positive infinity. So what I can say is then x is an element from negative infinity up to infinity. Remember, infinity always has round brackets. Okay, another way of saying that is simply to say x is an element of all real numbers. Okay, real numbers are anything between minus infinity and infinity. Okay, or anything that can be defined there. All right, and then our y values, our domain and our range. So that x was our domain. Range, let's have a look. Y is going to be a very similar story here. What gets mapped? Well, everything, if you follow this line on and on and on and on for all eternity, you'll go to minus infinity. And if you follow it this way, you'll go to positive infinity. So we've got the same looking range there. Negative infinity up to infinity, or y is an element of the real numbers there for range. Okay, let's have a look at the next one. So this is a parabola. And we look again at the direction that this is going in. So if we follow this onwards, even though it's at a bit of an angle, you'll see it is defined for all the x values all the way down to negative infinity. So the domain here is going to be x as an element from minus infinity up to positive infinity. Okay, which y values are defined here? Well, that's going to take some concentration. Let's see. We can have a look and see the lowest one. Remember to always go from smallest to biggest so you don't lose out on any marks. The lowest y value here is at 0, okay? And then this is going to go all the way up to infinity. Okay, so this one is going to look a little bit different now. What we've got is we've got y as an element from our smallest value, 0 up to infinity. We know that we can only have round brackets when we're dealing with infinity. But what we can take a look at here is the graph defined here at y is equal to 0? And it is, and so that means 0 is included in this range, and so that will be a square bracket there. Okay, there is another notation where you could say y is between 0 and infinity, and then because infinity is not included, there's no equal sign, and because 0 is included, you put an equal sign. That's also all right. So there are a couple of notation options, but you can say either this or that, and your teacher will understand exactly what you mean. Okay, now we're looking at this one here. It's a hyperbola, and so what we know about our hyperbola is that it's got 2 asymptotes. Okay, and this one, because it's just 1 over x, the asymptotes are here at the axes. Okay, so that's something worth noting. because it means that my x values are going to be defined from negative infinity all the way up to positive infinity, but not allowed to equal this asymptote, which is at 0. Okay, so x is an element of the real numbers, but x is not allowed to equal 0. Okay, and you'll notice the same thing happening here. Have a look at the lowest y value. It's going down to negative infinity. And then the highest y value here is going up to positive infinity. Okay, so the graph is defined everywhere except for here at the asymptote. And so now we can say y is also an element of the real numbers, but it's not allowed to equal whatever the asymptote is. Okay, that's not always going to be 0. That is going to be specific to whatever your asymptotes are. And then lastly there we've got an exponential graph, okay, and that one has an asymptote also here. In this case, because we're dealing again with just the parent graph here, we haven't shifted it anywhere. The asymptote is this axis, so basically when y equals 0. Okay, this, if you follow the arrow, it's defined all the way to minus infinity, all the way to positive infinity in terms of our x values. So x is an element from minus infinity up to positive infinity, but y is only defined above that x-axis there. So y has to be greater than 0. Okay, or you can write that as y is an element from 0 up to infinity. And remember, because it's an asymptote here, it's not allowed to be equal, and it needs to be a round bracket.